Oh, it's updating. This little spinning thing on the top right, that means it's going online and updating the image on in the cloud. So it's got to do its thing first. Anyway, when you're doing first aid, there's two situations you're going to have. One is the first aid on many of them may be the same. Like say we have lead sulfate and magnesium sulfate. Okay, the first aid is going to be the same. So instead of repeating the first aid on each one, to me, that's busy work. All you need to do is go lead sulfate, comma, magnesium sulfate. All right. So you're going to cut down your busy work a lot. You still have to do the first aid, which is important, but you're not going to be repeating it. Secondly, if we've done the first aid on this chemical in the past, you don't have to repeat it again also. Because we're covering lots of chemicals in these next two labs. I mean, this one and the next week. So if we've covered that before, then just say see lab 5 or whatever, instead of writing the first aid out again. Because the purpose of me having you do first aid is so you're exposed to the first aid in case you get it on you or inhale it or whatever. Okay, I don't want to burden you with a ton of extra work that's not necessary. I want it to be covered. Okay, does that make sense? Now, if you want to repeat it, that's fine. I'm just saying you don't have to. I'm not requiring you to. Some of you like to be very complete though, which is fine. Do it. Just like on the background, you don't have to do the background. The purpose of the background is to explain what's going on in the lab with some theory and that kind of stuff. So I'm not requiring you to do the background in your pre-lab. Some of you are, which is fine. I'm just saying I'm not going to mark you off because you included it. I'm just saying I'm not going to ding you if you don't include it. Okay, so the main thing is first aid, and you're covering a lot of chemicals in this lab. So you know, next week's lab we're going to have similar chemicals, if not the same, which is going to save you work. Because you just say C lab, is it lab 6 or 7? 7. I know the title's a lab, but the lab numbers I got. Okay, does that make sense? Yes, I can tell. Okay. Oh, you know what I should have done? Shoot. Okay, everyone, I want you to take a picture of this. I was going to print this out for you, and I flat out forgot. Let me focus it, make sure it's as crisp as it can get. And zoom in as much as you can. Don't worry about the title. Okay, the other thing you can do is I'll show you where it's located in Canvas here. Okay, so it's in unit 4 files. So if you want to pull that up on your phone. That would be the other way to do it. So it's in unit 4 files down towards the bottom. It's called solubility table. And I apologize for not turning that off for you guys. Okay, this is what we're going to be doing today. Now, yesterday we talked about single replacement reactions. And that's where we had a metal and the metal got either oxidized or reduced. Today, we're not going to talk at all about oxidation reduction. All we're doing now is we're going to do a swap. So we're going to swap the cations. So you're going to start with 2 ionic solutions. No metals involved, 2 ionic solutions. So if we had a solution AB and a solution CD, where A is the cation, C is the cation, B is the anion, D is the anion, we dump them together, then we're going to have a combination of the A's, B's, C's, and D. And now there's a possibility of a new combination. Instead of A always pairing with B, now A could pair with D. Instead of C always going with the D, now the C can go with the B. Okay, it's like switching partners. You're playing a tennis match, a dual tennis match, and then all of a sudden they're together, you switch partners. Okay, so you're switching one set, not both. Because you switch both, you end up at the same place. Yeah, so you're just going to do one or the other. One or the other. So I usually just say switch the cations because it's the first one. Okay, so that's the deal. Now the next question is, if you start with 2 solutions and I tell you they're AQ, that means they're dissolved. AQ stands for aqueous. Aqueous means that the cation and the anion are dissolved usually in water. They don't have to be in water. It could be in some other solvent, but normally when you talk about single and double replacement reactions, it's always water. So that's what the AQ means when you see it. It means this is solution in water. It also means that there's no solid in there. It's clear, not necessarily colorless. It could be blue or green or yellow, but you can see through it. That's what clear means. There's opaque and clear. Opaque means like milk. You can't see through it. Clear means it's like pure water. You can see right through it. So double replacement reactions are starting with totally dissolved cation, anion, or totally dissolved salt. So this is a salt solution. and we're dumping them together. So we're going to have a new salt solution. But we don't know if it's aqueous anymore. It may not be. So if I take one solution, pour it into another, and nothing happens, then the new solution is going to be still aqueous. It's going to be clear. It may have a color, may not. See through it. Okay. All right. Well, what happens if you dump those two together and something happens? Like you get a white solid. Now, next week, this is what you're going to be doing in lab. You're going to be doing solution A, solution B. Anything happen? Observation time. So next week's lab is going to be very similar to this week's lab in terms of dropper bottles and stuff. It's a pretty cool lab. Colors change or nothing happens. So the question is, how do you know? Can you predict? So it's the new combinations. So these are the four things that'll happen if something's happening when you dump them together. Color change. It still may be clear though, but there's a color change. Boom. Something's going on. Chemical reaction. Emission of light. Like you've seen the sticks where you break them in half and they glow. Okay, something's going on. Chemical reactions going on. Formation of a solid. When I say solid, I'm going to say solid, liquid, or gas. Any three of those qualify. Now, the problem with liquid is, how do you know the liquid formed? So if the liquid formed is also clear and also colorless, you don't really know it formed. Now, one of the major reactions we're going to study in this class, in the next unit mainly, is acid-base neutralization. So when you take an acid, you throw a base in there or an alkaline solution together, a reaction happens. How do you know? Heat's given off. Then you know something happens, even though it may not look different. So no visible reaction, NVB, but in the key there is visible. So something may have happened, you just didn't know it happened. Okay, and the major one is neutralization. So whenever you have a reaction and you notice it's an acid and a base being put together, like hydrochloric acid and sodium hydroxide or lye, that sucker is going to get really hot. You go, oh wow, something's going on. But you look at it visibly and it's just got hot because it's creating H plus OH equals what? H2O. So when you neutralize an acid and a base, you're creating water. And you start with a water solution. So you're creating water inside of water. So that's why it doesn't look like anything's going on. But the H plus and the OH minus are definitely combining. And water is extremely stable compared to the H plus and compared to the OH. That's why it forms so rapidly and why there's so much energy given off. It's because the potential energy, all that potential energy difference between the two is converted to kinetic energy, heat. So those are the four things that give away whether something's going on when we dump the two solutions together. Okay, let's go back to this here. It's tricky to predict without knowing much about this table. Now, when you go to 1A and 2A, you're going to have to memorize these 7 guidelines. And it's a pain. So to save you that pain, I've created a table that's very black and white and really easy to use. So going back to that new solution again, is the new combos solid or not? That's what that black and white table will tell you. So how do you use it? 2 fingers. That's how you use it. Okay. These are cations on the top, anions on the left. And where they come together is either going to be black or white. So say we have sodium nitrate is our new combination. Well, is that going to be a solid or is it going to not do anything? Fingers. So we're going to start here with 1 finger and the other finger is going to go here. And that's where they're going to meet. Is that white or black? It's white. That means it's not going to form a solid. It means it's going to remain clear. So sodium nitrate is going to be clear. Let's take sodium chloride. Fingers again. Okay. We go sodium chloride. It's white again. So when you take salt, table salt, and put it in a little bit of water, does it stay a solid? No, it dissolves. It becomes aqueous. Aqueous. That means no solid, no color change, no gas emission, no heat being given off. And look, it's white. So this chart proves your observation is consistent with the chart. Okay, let's take sodium chloride and silver nitrate. Now let's look at silver nitrate for a second here. Okay, here's nitrate. There's nitrate here, and go over here to silver. Okay, silver nitrate is white. That means a solution of silver nitrate you're going to be using in lab today and yesterday, and it's in an amber bottle, so you really can't see it. And the reason it's an amber bottle because it's sensitive to UV light. It's colorless and clear. Okay, let's dump a solution of sodium chloride and silver nitrate together. We have a double replacement reaction. We're going to swap out the cations. So that means the silver goes to the chloride and the sodium goes to the nitrate. We already know the sodium nitrate, nothing happens. Let's look at silver chloride now. Okay, we have silver, we have chloride, and guess where they're meeting? Black, solid forms. You don't know what color the solid is, though. You just know a solid forms. In this case, it's white, but it can be yellow. You're going to see next week when you do the lab, you're going to have different color solids form. The main thing is black, solid forms. Now, if you look at the guidelines, it says compounds of group 1 elements. Those don't hook up to anything to form a solid. And if you look up here, this is group 1, 1. Okay, and this is the other one it mentions. down here, and ammonium, NH4. Okay. They're all white. All the way down, they're white. That means they don't hook up with anything. It doesn't form a solid with anything, no exceptions. Nitrate, look at nitrate. Chlorite, chlorate, acetate. Those don't form up anything either. Those form part of the solubility rules down here. And there's some exceptions. That's the problem. So those are rules, then there are the exceptions. On the chart, you don't have to worry about that. Is it black or white? Okay, so does everyone understand how to use this chart? Bring it with you next week. Print it out and bring it with you. Or use your phone. Okay, does that make sense how to use this thing? Okay, I want you to know these indicators of a reaction. So, color change, light is generated, solid, liquid, or gas forms, and the absorption or emission of heat. Does it get hot or does it get cold? And this is the same thing as that, formation of gas. And remember, the formation of a liquid is an acid and base neutralization reaction, forming H2O. Okay, so let's talk more about aqueous now. Aqueous means that the cation is surrounded by water. The anion is also surrounded by water. So they're not touching. They're being insulated by water molecules. So if we look at water, oxygen is more electronegative than hydrogen. Remember we did the delta electronegativity? If it was greater than 0.5, it's polar. Okay. If you look at H and O in the electronegativity chart that I gave you and look at the difference, it's like 1.5. It's quite polar. And the arrow points to the most electronegative of the group. So oxygen ends up being partially negative, partially positive on the hydrogens. Now, what that little squiggly mark means again is it's partially. It's not a full-blown ion. It leans towards negative or it leans towards positive. So what happens is that cation, that sodium cation, the negative oxygen is being attracted to the sodium all the way around, 3 dimensions. Now, this is 3D, remember. So we made like a bubble around that sodium. And conversely, we've made a bubble around the chloride ion with the H's. Now, when we surround something with water like this, it's called a hydration sphere. And in fact, there are 3 hydration spheres, like an onion. They keep building outward. And they're called primary, secondary, tertiary hydration spheres. But for us, it's a hydration sphere. That's all you need to know, okay? And that's what aqueous means. Okay? Aqueous means surrounded by water. The water pulls that salt crystal apart. Now, question is, why do some things form a solid and other things don't? Okay, there are two forces here. First force is solvating force. Solvating force Okay, the solvating force pulls apart the ions in an ionic solid. And the ionic solid is a crystal, just like salt crystals. Okay, the opposite force is called the crystal lattice force. That's what holds it together. So this is like Star Wars, the battle of two large groups. The stronger one will win out. Okay, and we're going to abbreviate this as SF and CLF. So if the solvating force is greater than the crystal lattice force, nothing happens. If the crystal lattice force is greater than the solvating force, a solid forms. So when we dump those two solutions together, we're having two new combinations, and either one of those could produce a solid. Both of them could, or one or the other, if the crystal lattice force is stronger than the solvating force. Solvating force is temperature dependent. Crystal lattice force is not. God, I can't write today. So let's take some ice cold water, put some sand in there, and throw some salt in there. Ice cold water. We swish it around and we see that the salt crystals are still at the bottom and so are the sand crystals. And then we heat it up. What happens to the salt? What happens to the salt in the water when it gets hot? Dissolves. That means the solvating force is becoming greater as you turn up the heat, and it's pulling that salt apart. Or in super cold water, solvating force, because it's temperature dependent, is not as great as the lattice force keeping it together. So you can modify the solubility bit with temperature. And what you're doing is you're modifying the solvating force, not the crystal lattice force. Because that sand is still sand. Nothing's happening to it. If you get it hot enough, it turns to glass. Not ions. It doesn't ever become soluble. So the crystal lattice force in sand, silicon dioxide, is very, very strong. Well, the crystal lattice force in sodium chloride is not. So you heat the water up a little bit, it dissolves it away. Okay, so I want you to know the two forces driving solubility. Which is temperature dependent, which is not temperature dependent. Should be able to draw something like this. Should be able to draw a hydration sphere. All you're doing is you're surrounding cation with water, surrounding the anion with water. And that's what keeps them apart. Okay, that's the qualitative side of this double replacement reaction. There's also a quantitative part. Now, the quantitative part is split in two parts, Unit 2 and Unit 3. When we get into solutions, that's all double replacement reactions, and there's moles per liter, and it's very quantitative, very numerical, okay? Today, we're not going to do that. We're just going to look at the reaction part of double replacement. I need more room here. Now I got it. And whenever you do a double replacement reaction, you'll be doing three equations, three chemical reactions. First one is called the molecular equation. Second one is the total ionic equation. And the last one is the net ionic equation. Then also you need those spectator ions are going to be around as well. So spectator ions are in single and double replacement reactions. And remember that spectator ions don't do anything. They just go along for the ride. Just like if you're a basketball game, you're watching the basketball players, you're not touching the ball, you're not doing anything, you're just watching. So let's do an example, okay? Let's dump some solution of silver nitrate and a solution of sodium chloride. Solutions together, dump them together, boom. Okay, the question now is, we have two new combinations. And those combinations, do they form a solid or not? Do they form a liquid? Is there a color change? Is there gas being given off? Is there heat given off? Is light given off? Okay, so the new combinations are, we're swapping the cations. That means the cations get swapped. So the silver goes to the chloride, the sodium goes to the nitrate. We already talked about sodium always in aqueous form. So sodium whatever is always going to be aqueous. Nitrate's the same way. Okay, because everything under sodium and nitrate is white. No solids. However, with silver chloride, remember so the silver and the chloride come together, black box. So that's not aqueous anymore. That is an S for solid. Now, some books will call that a precipitate or a PPT. Other books will call it an S. So you can either put PPT there or S. S to me is more logical. It's S for solid. But technically, it's a precipitate. Okay, so that's the molecular equation. So we haven't split anything up into individual ions yet. Okay, so the first equation out of the chute is going to be the molecular equation. So you start with reactants. If the reactants are both solutions of ions, it becomes a double replacement reaction. If one of them is a metal, it's a single replacement reaction. So no metals involved, double replacement. Metals involved, single replacement. Okay. Then you swap out. So you're going to be starting with basically you'll be starting off with the reactants only. Then you're going to swap the cations to create the product. Then you're going to go to your solubility table or rules. If you'd like to get started memorizing those rules for when you take 2A or 1A, have at it. But for our class, you don't have to. You can use the table. Okay, so that's first step. Get the molecular equation down and figure out whether you have a solid or not. So it's going to be S or AQ. All right, next thing we're going to do is we're going to break apart all those ionic molecules into individual ions. Okay, so anytime you have an equation, chemical equation, is it balanced? So how many AGs do we have on the left and the right? If one on the left, one on the right. Good shape. How many nitrates, NO3s? One on the left, one on the right. Sodiums, 1 and 1. Chlorine, 1 and 1. So it's balanced. Inventory proves it. Okay, now once it's balanced, now we take it apart. And this is the part I'm going to warn you on where most people get confused. This is not hard. It's just got a lot of details. And the details is where you get lost. So all we're doing is we're pulling apart this thing. Okay. Now you also should have your common ion chart when you're doing double replacement. So next week, bring your common ion chart. And I have a few extras if you don't have yours anymore, or print one off at home. So we're going to take this silver. Bless you. The nitrate. Bless you again. Sodium. Chloride. Notice I'm writing AQ on all those. That's because that's the way they are in solution. They're really separated. They're not together. Okay, so that's the reactant side. Now, because it formed a solid, I'm not going to take it apart because it's a solid now. The crystal lattice force is making it a solid, really strong with silver chloride. Okay. So that is the the first one we did was the molecular equation. This one I just did is the total ionic. And let's abbreviate these. So this is going to be ME, TIE, and NE. Excuse me. And IE. So we've done the molecular equation, total ionic equation. The next one we need to do is the net ionic. Okay, the net ionic equation is, did anything happen when we put those together? Did a solid form, the color change, anything like that? Yes or no? Was the box white or black? We put the silver and the chloride together. The box was black. That means a solid form. That's why we have the S here. So something did happen. If something happened, we have to write the net ionic equation. If nothing happens, we're going to have null set. Okay, so the net ionic equation is we form silver chloride. And how did we do that? We added what to what? What are the two things we added to get silver chloride? Well, we added silver to get silver chloride. And we added chloride to get silver chloride. So that's the net ionic equation. It's much simpler. If nothing happens, in other words, we dump the two solutions together and everything's still clear and colorless, then we have no net ionic equation. And then we need to note spectator ions. Spectator ions in this case is sodium nitrate. So that's double replacement. So the details will get you on this thing. And on our next unit, we're going to talk about things like what's the concentration of the silver ions in terms of moles per liter. So notice how we keep going back to moles, moles, moles. Now, back in the old days, back in the 30s and 20s, when the CSI people used to do a lot of wet chemistry, this reaction here is how they tested for the presence of chloride. They would take silver nitrate solution, drop it into another solution, and if it changed to a white solid, chloride was there. It's called qualitative analysis, wet chemistry. They don't do that anymore at all. There's a special device that determines whether chloride is there or silver is there. It's called atomic absorption. It's where you heat the thing up to really hot. And then the stuff that comes off, you detect with an instrument. And if it's a certain frequency, you know chloride's there. If it's a certain other frequency, chloride is not there. It's called atomic absorption spectroscopy. So, spectroscopy. spectroscopy. That's what it is. Atomic absorption spectroscopy. Easy for me to say. Excuse me. All right. Are there any questions about this process? It's fairly straightforward, but just again, I want to emphasize, pay attention to the details. Things like whether you're writing aqueous or not, whether you got the charge there on the total ionic. Total ionic equation is the one that's a killer. Okay, so let's do another one. Are there any questions at all about this process? No hands are shooting up. Okay. Let's do one. We're adding. Let's add an acid and a base together. Okay, so we have a solution of hydrochloric acid, solution of sodium hydroxide, lye. I'm going to dump them together. Now we know something happens because it gets hot. So a reaction happened. However, the solution is still clear and colorless. You start with clear and colorless, dumping stuff together, no change, no visible change, but it gets hot. So we know a reaction happened. Well, what happens is the H and the OH form water. And then we have what's left over is the sodium and chloride. So we dump hydrochloric acid and lye together, we end up making water and salt. So if you were to taste that after it cooled down, it would be salty. So let's take the hydrochloric acid apart. There's H plus, Cl minus, aqueous. Take the lye apart, becomes sodium, aqueous, OH, aqueous. Now, because H2O is a liquid, or it could be even a gas, depending on how hot the water gets, it's going to be staying together. So that's why we write it together like this. We're not going to take it apart. And then what's left over is the sodium and the chloride, and those don't form a solid, so we have to keep them in aqueous part. Okay, was there a net ionic equation? Did something happen? Yes or no? 4 things. Okay, the solid form? No. Gas, liquid, or solid form? Yeah, liquid form, water. No visible light. Okay, so because water formed, we have to write a net ionic equation. That would be H plus AQ plus OH minus AQ gives us water. Spectator ions are sodium and chloride. Now, identifying a base and an acid, when we get into the acid-base chapter, I'm going to be defining those. Like an acid is if a hydrogen ion can be disassociated, it's an acid, or if the OH ion can be disassociated, it's a base. Bases are frequently referred to alkaline solutions. Like when you get into gardening, they'll say the soil is too alkaline or too acidic. Alkaline, same as basic. Modern chemistry doesn't talk about alkalinity much anymore. They talk about how basic is the solution. Alkalinity is a holdover from the old days where we had wizards doing alchemy and stuff. Alkalinity, big deal. Okay, so that's another example of double replacement reactions, acid and base. Now, identifying an acid, again, until we have the chapter on acids and bases, I'm going to tell you it's an acid or a base. I'm going to have you learn 5 strong acids, 2 strong bases, and a couple of weak ones that you run across. Like you probably already know hydrochloric, HCl. Probably already know lye, sodium hydroxide. Those are ones you probably already know, but there are others. Okay, so that's the basics on double replacement reactions in terms of the equations you have to generate. Now, I have practice sheets for you. And where is it now? This guy here. So it says molecular, when it says complete, it's total ionic, TIE, and then net ionic. This is a double replacement reaction worksheet. And it starts off in the beginning by filling in quite a bit, and then towards the end, you have to fill it all in yourself. Also, there's your book explanation of this as well, with example problems and problems at the end of the chapter as well. So you've got a lot of opportunity to practice. Your lab next week is also going to have lots of examples of writing these equations. So in lab, you'll have opportunity to practice this as well. So what we've talked about today is a description of what happens when something goes into solution. What are the factors that keep something from going into solution or forming a solid? Remember the crystal lattice force and solvating force. And we also talked about the 3 equations involved: molecular, total ionic, and net ionic equations. Next week, we're going to be talking about what happens when you have 15 grams of something, it reacts and gives you 10 grams of something else. You're going to be actually working through all that. Okay, so any questions about so that was in Unit 5. Before class started, we were talking about whether we should go back to 5 units or 3 units, keep it at 3 units. So this is the first time I ever taught this. I've taught this a number of times. The first time I ever taught it with 3 units. Most of the time it's 5 units. But that gives you 5 tests you have to do. That takes away 5 lecture periods, unless they're online. And I'm debating which is better. I don't know. Some people like she was saying, Kathleen was saying, she likes 3 units better. Says it's more focused studying, but not as many. It really depends. and what you want to get out of the class. Okay, another thing is someone asked about practice tests. So these tests are all based on having 5 units. So there's tests, example tests 1, 2, 3, 4, 5. So what I'm going to do is go through these and kind of make up a practice test for unit 2, made up of units 2, 3, and 4 from the old days, because it's confusing otherwise. Okay, so that's a to-do on my side. Okay. That's double replacement reactions. And you do need to practice that. If you do the pre-lab for next week, you're going to be getting into the double replacement concepts as well. So that'll be a good review for you. All right. Anything else? Everyone's going, please, no.